Yeah, so I work for those of you who don't know me, I work across the street in CSAIL on spoken language technology. This problem of unsupervised learning is one I've been interested in for a long time, since my graduate school days, actually. The idea of trying to get a machine to learn a language, to me, is a fascinating problem, very hard one. Starting about 10 or so years ago, I sort of came back to this issue with some of my students and looked at audio-only processing, seeing where we could look for reoccurring sequences of sound in any arbitrary language and try to discover word-like patterns from that. And that sort of coined the term spoken term discovery, because you don't really know what you have in a large body of audio. And we've done some other work with former students like Jackie Lee, trying to learn units, phonetic-like units in an unsupervised fashion, or even subword structure using Bayesian non-parametric techniques combined with adapter grammars, things like that. This work today is a fresh take, and this is based on the doctoral research work that David Harwath, a student of mine, has been doing, and it takes a fresh look at unsupervised learning of speech and asks the question, well, what happens if you have another modality that you can try to leverage as a weak form of constraint? And in our case, we're using images. Now, I should say that, you know, I'm fascinated by learning language by machine just because I think it's an interesting problem. I think there are practical reasons why you might be interested in this, and one of them is the inherent challenge in facing automatic speech recognition. You know, there's about 7,000 languages, depending who you talk to, that are spoken around the world. Admittedly, many of them have small numbers, and the numbers are dwindling, but there's over 400 that are spoken by more than 1 million people. That's pretty significant. You know, industry has come a long way with a tremendous amount of work. I think Google claims they support around 80 now. But if you look at what they support, there's about a dozen different versions of English and Spanish and Arabic. So I'm speaking Canadian English, actually, so hopefully you can use Google Translate if you can't understand me. So, you know, there's a lot of work in doing that, and I think Brian will talk about this more this afternoon. We were part of this program called Babel that was trying to address low resource speech recognition issues. What happens if you have small amounts of data? But it would still take about a year to get the data and get it annotated and cleaned up. Pronunciation dictionary, things like that, for us to do the work on it. The goal of the project was to produce a speech recognition in a week, which was kind of ironic because it would take the majority of the time to get the data. So this is a fundamental problem, and I think the issue is even worse for translation, which historically has required, it's an n-squared problem. Typically you use pairs of languages. So I think it's interesting to think about what can we do to move away from the current paradigm where you need these annotations in order to train up the speech recognizer. And this is just a schematic I put together to think about the different ways, and I'm sure there's many others, you could make the problem harder, moving to have less human intervention or expertise and maybe more learning on the machine side. And up in the upper left is sort of where 99% of the speech recognition research has historically been, where you get a large annotated corpus and maybe some associated dictionaries. More recently, people moving to grapheme-based or character-based approaches, but you still require the parallel speech and text. Down here are more challenging problems. One is, well, what if you have a large body of audio and a large body of independent text, but you know they're the same language? Can you leverage that? That's kind of like a decryption problem. And then the hardest one, I think, which is moving more towards more human-like scenarios, is what if you're just immersed in the world and you can perceive, different modalities. You can hear, you can interact with other people, and you can see, and things like that. So the unsupervised learning work that we'd done in the past was down here, but it was just using speech. And if you're giving it large repositories of lectures or things like that, it's a very hard problem to try and expect a machine to learn from that. So what David is doing is, what if we combine speech with visual inputs paired somehow? So that's what I'll be talking about today. Now there's another motivation when you start thinking about combining speech with vision, and that's, well, if you think about robots of the future or other cognitive devices that are going to be perceiving in different ways, it's going to be, if you want to interact with humans, it's going to be important to be able to convey things that you sense into language. So vision. Talk about what you see and relate that to the human, or if the human's talking about something that you see. Imagine you're driving around in your self-driving car or whatever, talking about things outside the window. So you want to be able to relate things like, well, this is if they're talking about the church here in the spectrogram, relate this thing to the semantically what you see in the image, or street over here, relate that something like this. So it's an interesting idea to see if we can relate information in the visual stream with that in the speech stream. And this gets at sort of the semantics, underlying semantics, because now you're not using any kind of other text information. So the key idea David came up with was to think about if we could learn a speech, vision, embedding space. Other people have talked about the notion of an embedding space here. It's certainly popular these days in the NLP community, representing words as vectors, or sentence or other concepts, even documents, as some kind of vectors. And the point is that in this high-dimensional space, that semantically similar things would occur as similar points in the space, whether it's days of the week, countries, or numbers, things like that. This is a popular notion in the machine vision community as well, where the idea that similar objects or images with objects ultimately reside in similar points in the space. And David's idea was, well, can we learn a network where we have the parallel streams of the speech and the image, and learn an embedding space where speech that's talking about things that are similar to what's in an image learn to be in similar points in the space. That's the key idea in a nutshell. Now, he explored a number of different networks, but one of them that I'm going to talk about today, again, was a parallel architecture. On the left-hand side, we used a open source VGG 16-layer network that was trained up on ImageNet, and we took off the top layer initially and added another transformation that we would learn. And then David created a hierarchical structure of convolutional networks that would process some length of the speech, and he was limiting it to, say, 10 or 20 seconds of speech, but we could scan over it and successively downsample, and ultimately, in both cases, end up with a high-dimensional vector. Yeah?
So was on the left, it's the top hidden units or the top output?
No, we discarded the output layer, and he learned another projection. So we were ultimately learning a 1,000-dimensional projection of the two together. And the idea would be that you would use a dot product as a notion of similarity. The vector in this case was at the highest layer here, we had a 1,024 feature maps, and then we would do a mean pool over time over all of them to produce a 1,000-dimensional vector, and the output of the ImageNet would also be a 1,000-dimensional representation, and you would take the dot product, and ideally when the image corresponded to the audio, you'd have a high value, and when there was a mismatch, you'd have a low value. And we constructed a loss function from that, where you would have a matching pair of an image and a corresponding spoken description, and then you'd give it some mismatches, a mismatching audio description and a mismatching image to the particular spoken description. And from that, we could learn the parameters of the network and the transformation. Now to do this, we needed data because there wasn't data that existed. There's annotated Flickr data for text, and we actually started with that. We had people record the captions, but some of the captions are a little, you know, how people type is not how they speak. So ultimately we wanted to just get recordings of people. We said, describe this picture in 2 or 3 sentences. So we made a mechanical Turk task, and we used the MIT places corpus that Antonio Torralba and Ode Oliva had created, which has millions of pictures, and we just made a little mechanical Turk task and recorded the audio. So that's still ongoing, and by the time we had about 120,000 annotations, we could train up the model, but subsequently, every time we get more data and retrain the model, it does better. Now, to evaluate the behavior of this model, we sort of copied an approach that had been used in the image text, folks doing analyzing image captioning, whereby you take a set of images and say 1,000 images and a set of 1,000 corresponding captions, and you give yourself a caption and you say, which is the image that corresponds to this description? Or you can take an image and say, which is the caption that corresponds to this? Now, in our case, we modified it because we were giving it the speech waveform. So we had 1,000 images and 1,000 corresponding spoken descriptions, and we were saying, for this speech, which is the image, and for this image, which is the speech? And we can evaluate that and report on that. Let me show you some examples of what we were trying to do. And I'm going to ask the audience a question here, so pay attention. Okay, so up at the top, we have a spectrogram of an audio, and just for readability, we have the output of the Google Recognizer on that. And I'm going to have you listen to it, and then tell me which of those 5 pictures you think it is.
Photograph showcasing a pool at some sort of a tropical resort. In the backdrop, there's a bunch of tropical trees and what appears to be a bunch of other buildings or houses.
So if 1 is on the left and 5 is on the right, which one do you think it is?
4.
4? Or 1? Okay. I don't actually know. That was just to get you to pay attention. But this is the top-ranked 5 pictures, and so you would see if it was in there. Here's another one.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
Okay, that one's probably you're more confident. Yeah, it's probably 2. Okay, so this is the idea of the test, and we can evaluate the performance. And David had a NIPS paper last December, and I think it was about 0.3 in the top 10 for the image recall. This is this task. And then the caption recall, which is this is a little less intuitive, where you show a picture and you have to figure out which caption it is. I think he was getting about 0.2. With his latest stuff, he's doing much better. He's up around 0.48 for both of them. So the fact that 48% of the time you have the right image or the right caption in the top 10 out of 1,000 is a good indication that it's learning something, okay? So the question is, well, what exactly is it learning? And now we want to dive down. And we had a clue that there was something interesting going on when we took off that mean pool layer. Yes, Karen?
I was just curious if you use the text, if you tried using the text at all that the recognizer produces, or how that would do.
It's a good question. So it's not exactly, it's apples to oranges comparisons. Other people have evaluated on image to text that retrieval task, and the numbers that we're getting are in the same range, I recall. Is that still a fair statement, David?
different data sets.
Yes, of course, it's different data sets, but the numbers are in the range. So you're right, we could do that. We haven't done it yet.
There's a lot of people publishing who can't do that.
Yes.
So
Yes.
it's on the list.
So we took off that mean pool layer at the very top, and so then what happens is you have a 1,000-dimensional vector at every point in time, every 10 milliseconds in the audio, which is more like the conventional speech recognition situation. And you can compute a dot product every 10 milliseconds. And you can see how the dot product fluctuates as a function of time. So it gives an indication of where in the speech signal, in the spectrogram, it really resonates with the picture, okay? So again, just for legibility, we have the time-aligned Google transcript on top, and I'll play it for you too.
A baseball player from the Mets pitching a baseball.
So you can see the fluctuation here. Baseball seems to really, resonate well with this image, which would make sense. And Mets, pitching, and baseball again. Here's another one. A man riding a bike down a wooden trail in the woods. You can see it's kind of spiky. And here's another one. Image on a boat, and there is a set table with some red folding chairs. And again, you can see there are regions in the signal where it likes it. So this made us think that there were particular points in, yeah?
Does it tend to particularly like things that correspond to ImageNet classes?
That's a good question. I don't actually know. The ImageNet had 1,000 topics because the ImageNet, it was trained in a supervised way. Although the more recent work we're doing, we're taking off more of the layers and doing a full training, and that seems to help improve the performance, but it is giving it a start. Certainly, you can say that it's learning objects, and I think we'd have to move to something like video to learn other types of attributes. So, but that's a good question. Getting back to this, though, that we had a sense that there were particular things that were resonating with the images. And so what we did was we took some of the data and we did a forced alignment. So we had an estimate of where the word boundaries were, and we took a bunch of words, a dozen or so, that had a lot of data. By the way, these are all spoken by different speakers in different recording environments and stuff like that. So the AudioNet had to cope with all of that. And then we saw where the points lay in the space. And this is a two-dimensional projection using TS&E. And you can see that, for the most part, similar words or the same word spoken, different instances of the same word occur nearby each other in the space, which again was encouraging. There's this noise right in the origin here, but we can ignore that for now. But otherwise, you can sort of see there is some nice clustering going on. So the embedding representation that we're learning does seem to be doing things like speaker normalization somewhat, which is nice. So the next thing we wanted to do was to say, well, so in this case, these vectors were based on knowing the segmentation produced by a speech recognizer. We wanted to get away from that and see if we could discover words automatically in both the speech and in the images. So in the case of images, we wanted to see if we could figure out that this little portion of the speech, which corresponds to lamb, was very highly matched to this sub-image here in this picture. Now, that picture doesn't have much else besides the lamb, so that's not very interesting, but you get the idea. And also, many different instances of lambs or different speakers saying lamb in different contexts. So the way David started to do this was to, on a given pair, so an image and its corresponding spoken description, we considered a large number of combinations. We sub-segmented the image into several thousand possible sub-images that had a reasonable aspect ratio. And likewise, we could just subdivide the speech recording into a large number of possible candidate subsegments. And then we could compute, so it's an n-squared problem, but it's only on one pair. And then for each possible pair, we could compute that dot product. And then from that large set, millions of candidates, we could select the top few best candidates. So let me play this particular one.
Seaside picture. There are several seagulls floating in the water. The skies are clear, and in the distance is a white lighthouse.
Now, in this case, and there was some filtering done to narrow it down, there were 3 really good segments. This, and the color coding is the same thing. So over here, the word seaside, the orange part, correspond to this orange box really well. Here we have the word water in yellow, which mapped very well, had a high dot product with this subsegment here, and over here we had lighthouse in red, which seemed to like this sub-image there, okay? So we could go through this for all of the data, every matching pair, say, well, what are your best candidates? And we ended up with over 1 million of these. And the nice thing about this, if you think about it, it's scalable because it's linear in the amount of data. All this operation is just being done on the matching pair, okay? And then we threw it out and we did some k-means clustering. And you can do clustering on the sub-images using that vector representation, and you can do clustering on the audio segments using the audio representation, and then you can make links between the two when you know that there are matching pairs. And let me show you some examples of what we see. So this is some instances of one of the clusters, okay? And I'm going to play for you some instances of the audio cluster that was linked to this cluster.
Castle.
Glitch, let me.
Castle.
The castle had
Castle
on the couch, round couch.
and a couch.
Sunset.
The sunset,
The train.
the train,
The wooden.
Wooden.
The lighthouse.
a lighthouse.
A lighthouse.
These are more. You know, you can get as many as you want. You get the idea there's something going on here. You know, cockpit, stairway, mountain, bridge, church, and maybe building, things like that. So this is a large table of numbers, and I apologize, but I want to, this is the top 50 audio clusters, the variance of the cluster. And there's a few things I think that are interesting to look at. Each row here corresponds to one cluster. So here's the variance column here. So they're increasing in variance as we go down. So to come up with a label for each cluster, we just took the majority vote of what the recognizer thought the word was underlyingly. So that gives you an idea of what word roughly we think it is. This column here shows the number of audio segments that fell into that cluster. So they're typically in the thousands. This is the number of image subsegments that fell into the corresponding image cluster. So these are big clusters, and this is scalable. So this isn't a toy thing, I don't believe. This column, purity, how many of the underlying audio segments actually had the same annotation. So a lot of the purities are pretty good. This is better than we were getting, I think, in the audio clustering work we did earlier. And this is borne out because, you know, we did some query by example experiments using this formulation, and it did much better in that task than any other prior result that we've done. And this is just showing the coverage. So, you know, some of the clusters have high coverage. So this one has 2/3 of the instances of desert. It doesn't really bother me so much if there are multiple instances of underlying words. So this is ranked, and so you get the idea of what we're talking about here. Now, another thing that we did is we wanted to see how the data was distributed, how the underlying clusters were distributed. There was some discussion today of the embedding space being semantic or more syntactic. And I think we have a bit of mix of both. So, here we have multiple instances of the word people. Again, this is on the speech cluster, so they're all on the same point, which is nice. You do get some things that I've circled in red that are not semantic. So tower and shower, but you get tower and castle and cathedral and church, archway, building. Here's book and boat, hallway, highway. I think ceiling is probably matching like ski, and we have windmill and window. So, those are not, well, probably not semantic, and it's more that they sound alike, that they're ending in the same space. So it's a bit of both, but it's encouraging that there is a lot of semantic. Yeah. Underlyingly, yeah, they were trees. That's right. So we're not getting 100% coverage. Some of the coverage is lower, so we're having multiple instances of it. Yeah, Karen. Yeah.
If you look at the words.
Yeah.
Times examples of those in the same cluster.
That's a very good. So it's a very good question. I don't know the answer. Have you looked?
To that kind of stuff.
The other thing we're dealing with is an errorful transcript. It's a hard task. The Google Recognizer does really well, but it's still a difficult task, and there's a lot of errors. I think it's about a 20% error rate. So that's a factor in the analysis too. So let me show you what David is looking into right now. It's the notion of a spotlight. And he's gone, so the interesting thing about the image branch is it's actually a convolutional neural network too. It's successively subsampling. And it has an idea of, we have a representation which is a 14 by 14 underlying quantization of the image. Take dot products with each of those with the speech as we go along. So when you play the speech, you can actually show where in the picture during the speaking is showing the high correlation. So it's almost like the computer can show you what it really likes in the picture when you're talking about it. If we got this working in real time, which it's actually possible, I think it'd be a lot of fun. So I'm going to play you a movie, and you'll see, it's the lighthouse one again, and you'll see smooth white blurs that correspond to the regions that seem to be resonating with the speech roughly at that time.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
Got clipped, but you get the, okay. So that's really what I wanted to talk about. It's an interesting, it's a great step forward, I think, in trying to think about how to combine speech with another modality like an image. For me, it's part of the broader picture of trying to figure out how we can learn language with less annotation. And I think the David framework works very nicely. It seems to be working, and we seem to be able to learn word-like units. And I think it opens the door to a whole bunch of interesting research problems in the future. As I mentioned, we've done work with trying to learn unsupervised units in the past at different linguistic levels, as have others. And I think we want to look much more closely at what on earth is going on in that convolutional structure of the speech. Because our intuition is it's got to be organizing itself into reasonable type units. So we'd like to find out what those are. As I mentioned before, there's no reason you can't do this by watching videos. And so that's something that I'm talking with some of the machine vision colleagues in our lab about pushing forward on. There's no reason we couldn't potentially think of ways to incorporate additional modalities. You know, things in the world make sounds, as we all know. So why couldn't you see something, you hear what it's doing, and you have somebody talking about it? You know, use all of those types of things to help with the learning. I think anything is fair game. And by the way, the analogy I bring to think about this kind of research is, as had kids or read to kids, you know, you're reading a picture book and you're talking about it, things like that. That's sort of the notion of what we're trying to get at here. That task is very natural for people to do, and we're thinking about ways to make it more accessible in different parts of the world so we can collect more languages. You know, it's very tantalizing, but we haven't connected all the way to speech recognition yet. There are people who've done interesting work with embedding vectors and things like that. I think we're close to being able to do that. What if, for example, you told the machine the written representation of the clusters that it learned? Can you use that to seed some learning of acoustic models and then generalize? And what if I said, okay, you can have this 10 years of newspapers or whatever you want to, you know, tell you more about the text representation. Can you make the linkage between the two and boost yourself up to have full-scale speech recognition? It's an interesting idea to think about it. I mentioned other languages. I think that's something that we would like to do. We're starting to collect other languages. I think Joshua talked this morning about generation. I think you can expand this idea. I mean, this is one particular network where we're just taking two inputs and saying these are the same or different, but maybe you want to be able to, from a speech input, generate an image, or from an image generate a spoken description, much like text, and connect them all. I think that's an interesting idea to consider. And even more crazy, I think it might be feasible to try and do some kind of machine translation and use the image as a form of interlingua between different languages. And that, if that were the case, break out of the n-squared problem that you're currently in machine translation. Although there have been some interesting recent developments on leveraging from multiple languages pairs to learn connections between new ones. I think there's many more interesting ideas. These are just some of the ones that we're thinking about internally. Thank you very much.